Okay. My audio is on, and welcome. Today, just a short 20-minute lesson on sinusoidal models, a sine and a cosine function that are basically shifted and stretched to fit a certain scenario. In particular, we'll be talking about average monthly temperature and how that is periodic, changing over time with the pattern. So where does this sinusoidal stuff come from? It comes from transformations of graphs. So if you're given a graph or a function y equals f of x, that of course corresponds to some graph in the xy plane. Then we can shift the graph with a transformation so that we move it around and we might stretch it or we might compress it. Maybe it's down here now and it's compressed in the y direction after we do a transformation. So there's three types of transformations we can do, and we always do them in the same order. R, S, T. The same order as they're spelt in the alphabet. This stands for reflect. This stands for a stretch or a compression. And this stands for a translation, shifting it up or shifting it down. We always do it in the same order, R, S, T. Okay, well, let's look at a specific example. Say we're given y is equal to x squared. This is a parabola like this through the origin. And say we wanted to shift it. Say I want to shift up by 2 units. I want to shift left by 3 units. And I want to stretch in the y direction. I'm just making these numbers up. 5 units. What would the new graph look like? And what is the new formula for the graph? So first of all, it looks like a parabola that was shifted. We do the translations last. So if you first stretch it in the y direction, it'll look like this. Now that we've stretched it, we can translate it, shift it left 3 and up 2 so that the new vertex is over here. It's useful just to sort of pick one point and see what happens to that one point. See what transformation happens to the vertex, and we get a graph like this. Now, what about the formula? Well, shifting up by 2 means we can take x, or rather shifting up, so we'll take y, and we'll replace it with y. If we want to go up, y minus 2. If we want to go left, we'll shift x by x plus 3. So it's opposite. If you want to go left, you go plus 3. If you want to go right, you go minus 3. It's sort of opposite of what you would think. And to stretch it in the y direction, it's also opposite. You take 1/5 y. What do these arrows mean? Well, it means that you replace the variable with the right-hand side of the arrow. So the new function, if we first do the stretch, right, we'll have 1/5 y equal x squared, which means y is equal to 5x squared. Okay, that's a stretched parabola. And we'll do the 2 shifts. So y will get replaced with y minus 2, and x will get replaced with x plus 3. Solving for y, just to get a nice final answer, 2 plus 5, x plus 3 squared. So when you move the 2 over to the right-hand side, you can tell, okay, yeah, it does shift it up by 2 units. We're adding 2 to the previous function. But when you look at it as transforming y, it's y minus 2. to move upwards. Yeah. So if you took any general parabola, and this is what we're going to do with sinusoidal functions, but you can take y equal x squared, transform it with RST, and you end up with the following function, y equal m x minus a squared plus b. 3 parameters to define a general form of a parabola, general form. You could use this general form to fit the data. For example, in physics, when we measure the height of a ball, h of t, we know what the constants are. It's negative 4.9 t squared, that's your x squared, and then your initial velocity v naught, and then your initial position h naught. Right? To fit this to the data of the ball, you just adjust the parameters accordingly. So that's exactly what we're going to do with a sinusoidal function. We'll have some data, and we want to fit the curve by choosing these constants to make it fit the data. Okay. So the next mini lesson is the trigonometric functions. So I'll move this down a bit. At this point, I would ask, are there any questions or anything else that you'd rather be going over other than this? Is this all making sense? That kind of thing. During an actual session, the student will be able to use the whiteboard, and I would encourage them to solve problems on the whiteboard while I'm there with them. I like to have a mix of me solving and them solving and asking questions back and forth. That's ideal. Okay, so trigonometric functions, meaning sine and cosine functions. Trig functions as models. We have the graphs of these functions. Y equals cos of, I'll use t, cos of t. This is the t-axis. The way I remember it is cos of 0 is 1, because if you looked at a right angle triangle that had an angle that's really small, the cosine is 1. So that means at time 0, it's right here, right? And then it's a periodic wave. It repeats itself right here when it's back up at the top again after 2 pi units. That's just a fact about these trig functions. Now, sine of t is exactly the same shape as cos of t. It's just shifted over a little bit. The way I remember this is the value at 0, sine of 0 is 0. If you look at a triangle with angle almost 0, the sine is 0. It goes through the origin. Otherwise, it looks just like cos. They both have a maximum and minimum value of 1 and -1 for both of these. It maxes out at +1 and a minimum at -1. Okay, so we have these two basic trig functions, and we want to perform the transformations. So what does the sinusoidal model look like? Sinusoidal model. We're just going to take our trig function, sine or cosine, doesn't matter. Either one will be okay, and apply the transformations. So capital T stands for temperature, equaling a constant M, let's call it C for the center, plus a constant A for the amplitude, and then cosine or sine. I'll use cosine of omega t plus phi. Okay, this is the master formula for sinusoidal models, trying to model nature with trig functions. C is the center of the trig function, where sort of like the middle of everything. I'll draw a picture in a second. A is called the amplitude of the model. Omega is called frequency of the model. And phi is called the phase or the phase shift. It's just a shift to the right or to the left, right? And C is a shift up or down. A, which might be negative, would be a reflection if it was negative, and it's changing the amplitude of this thing. So the sinusoidal model, instead of being a perfect cosine function, it's going to be offset with a phase, and it'll have different, it won't be 1 and -1 anymore. You'll have T max and T min. The center is sort of the center line right here. It's the midpoint between T max and T min. So you can figure this out the long way, just kind of looking at it and saying, oh, well, I can find the center, and then I can find the amplitude once I have the center, right? It's just the distance from the center to one of the T max or T min. So I could probably work it out kind of in my head, but I'm going to show you it's nice to have actual concrete formulas for these. There are concrete formulas that we could use that would work every time. Definitely you could use these for C and A because they're very intuitive. The formula for C, it's the center or the midpoint. So you take T max plus T min divided by 2. That gets you the midpoint of any two numbers, smack in the middle. For the amplitude, we would start at T min and we would start at the center and subtract T min to find that out. So start at the center to subtract T min. So T max minus T min when you do the algebra divided by 2. And that's sort of intuitive as well. It's half of the distance to the center. Okay, so nice formulas for these. There's also a beautiful formula for the frequency. Very useful. Frequency is 2 pi divided by the period. The period, in our case of monthly temperature, is going to be 12 months. It's however long it takes for the cycle to repeat itself again. And then for phi, I would just say there's no real general formula. Just look at your graph and shift it. Just do a horizontal shift, whatever you need to make it be a cosine graph. Because the minimum is not going to be, or the maximum is not going to be at time 0. You have to shift it so the maximum is not at time 0, but at time 2 or whatever you want the maximum to be. Okay, let's see how this all works. Let's do an example. So we've got our sinusoidal model. We've got some formulas. Any questions so far? If not, let's finish this. We've got about 6 minutes left with an example. So average monthly temperature in Toronto, let's say, downtown Toronto, is maximized, has a minimum rather, in February and to avoid negative signs, we'll use Fahrenheit, 20 degrees Fahrenheit, and this is actually the average temperature in February in certain years. And yeah, and it has a maximum, the average monthly temperature 6 months later. Maximum in August of 80 degrees Fahrenheit. Then, of course, assuming that temperature is a nice sinusoidal model, which it isn't, this is just a model for reality. It's not actually going to be the right answer, right? It's just an estimate or a prediction. So maximum in August. So then find, assuming a sinusoidal model, sinusoidal Like if you were trying to predict the stock market, then a sinusoidal model wouldn't work. It fluctuates too much. But when we're modeling something like temperature, monthly temperature moving around the sun, there's a fixed period to that. And it's always kind of the same year after year. So it's a decent assumption. Assuming a sinusoidal model, find temperature and av temp in April. Use the model to say, okay, what is it in April? What's the temperature in April? Okay, so the solution, we start with writing down the model. So step one. Step one, we need to define what our time scale is going to be. So easiest thing I think would be T in months that have passed since December 30th. So if 1 month has passed, you're on January 30th, 31st, and you've measured the temperatures and you've got your average temperature taken at the end of the month. So, 1 is January, 2 is February, etc. 3 is March. 4 is the one that we're asked for, April. ... 8 is August, right? The 8th month. And 12 is December has passed, and you're back to 1 again. So we select our time scale. Now that we have that, we can draw a diagram. Step 2, diagram. Okay, this is pretty important. You can figure out a lot from the diagram. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 1 month, 2 months. I'll draw it up here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 13, 14, back to February again, 15, and so on. The minimum happens at month 2, right? So the minimum's down here. The minimum value is 20. Okay. Then it has a maximum value at August, 8, and the maximum value is 80 at 8. Then it'll come down to 12, and then at 14, it'll repeat itself again. It'll be back down at its minimum value again. So you see that the period is 12. So, okay, step 3, write the model. Write down the model, just write it again for memorization. T of t equals center plus amplitude. Let's go with a cosine. Omega t plus v. Okay, step 4, find these parameters. Okay, the constants, a, c, omega, phi. We need to find these constants. Well, let's use our formulas. So c, remember, is going to be t max 80 plus t min 20 over 2. That's 100 over 2. That's 50. 50 is the center. Okay, then the amplitude is 80 minus 20 over 2. Okay, nice, easy formula. 60 over 2, 30. So if I look back up at the diagram, the center point is 50 and the amplitude is 30. So the center point right here is 50, not 0, but 50. And then it's 30 for the amplitude, right? 50 plus 30 is 80. 50 minus 30 is 20. So it makes sense. Okay. Then let's use our frequency formula. That one's very useful. We have the frequency is 2 pi over the period, and as I already mentioned, that's 12 months, right? So pi over 6. Now the only one we have to do is the phase. That's all that's left is the phase. Well, look up at the graph and notice that the minimum is at time 2. So take a cosine graph and shift it to the right. So for phi, we need to shift right by 2 units, right? We take our cosine graph and shift it right 2 units. Step 5, we write down our final answer for our model. So T of t is equal 50, the center, and then it's actually a negative cosine graph, so minus 30, right? Because if I'm shifting that February point over to the origin to be the new minimum, right, then I shift it by 2. But then I produce a negative cosine, not a positive cosine. So cosine of omega t pi over 6t, but then t gets shifted to the right, so t minus 2. That's a right shift. Yeah, t minus 2. Yeah, so if you want, we can write it again as 50 minus 30 cos of pi over 6t minus pi over 3. If you really wanted to know what the phase was, the phase would be minus pi over 3. Of course, this isn't a unique answer. We could have used a sine and got something similar. Or I could have used a positive cosine instead of a negative cosine. Just the shift would just have to be different. So there's multiple possibilities, but we're pretty much out of time. I'll just leave it as an exercise. Do the same example, but solve for phi and w. So say t of t is 50 plus or minus 30 cos, or say you had plus 30, you wanted it to be plus 30 for whatever reason. You can do that, and then you'd have omega t plus phi. And say you didn't remember my formula for 2 pi over period, or you couldn't quite figure out what the shift should be, then you can, as an exercise, find omega and phi via information that we have, which is t of 2 months is 20, and t of 8 months maxed out at 80. You can solve a linear system for omega and phi, and there you go. If you forgot my formulas, you can always recover it just by sort of common sense. Okay, well, thanks for your time. We'll end the lesson there. Have a good day. Bye.